Hello, my name is Carlos. I'm from Brazil. I'm very happy to participate this event. I'm studying the University of São Paulo in Brazil, and we developed some research about the animation, facial animation, blend shapes, about this technology to use the captures, capture the body, the face, and create a virtual characters, environments, etc. Okay. Uh, I will try to bring some information about facial animation and who we can use the artificial intelligence to create a virtual face from a video or photo captures. Okay. The agenda for this presentation is have some topics. The first topic is about the facial animation. I'm going to try to bring some details about this technology. And in the next, I'm going to bring a traditional approach about the facial animation because this technology is not old, but it's not new. It's middle, okay? And there are a lot of different approaches for this kind of technology. And the next, I'm going to try to introduce some concepts about the machine learning and follow this this information. I'm going to try to show how can I use the machine learning in the facial animations. Nice. And in the end, I'm going to show some examples about this. And okay, go ahead. Facial animation, the interest about this technology are growing in recent decades, okay? But it's not a trivial task because it's necessary the high accuracy, okay? And to generate a realistic face, because if you not create a realistic face, it's you can we human beings can detect very fast the problem. Okay, and let's see a little more about this in the next slide. Nice, but the idea the idea behind this technology it's bringing 3D face to life. Okay, in this case, the principal problem to resolve is it's transport an actor face to a virtual face. In the end, the idea is generate a virtual face looks like the capture. It's the principal problem to resolve. But what's the problem? There are a lot of problems when I try to create the virtual face. The first problems it's necessary to create a convincing facial animation. But the the human head have a complex and sophisticated structure, okay? And but I think the big problem is the human being is trained to identify expressions, okay? And this training starts when we are a child. And in this case, making facial animation a very complex task because tricking the human eye is not a trivial. Okay. There are a lot of use from this technology, but I think the principle is the movies and the games. Okay. There are several films where facial animation is used. For example, Avatar and the Lord of the Rings, for example. In the Lord of the Rings, we have the Gollum. It's a very famous character from these movies, and we use a lot of this technology in this construction for this character. Okay, nice. But there are, when you're going to create this this facial animation, there are some steps you need to follow. The first step is modeling. The second is capture. In the last is retarget. Okay, I'm going to bring some information about these steps next slide. Okay, in the modeling steps, there are two approaches. There are a mesh deformation and the blend shapes. Mesh deformation is when you create a only single mesh and you use this mesh to create all the virtual face. And you need to deform this mesh and they create this expression. It's this tech, this approach. It's common. But it's not very fast. It's slow. And in the other hand, there are blend shapes. The other approach, very common too. What's the meaning of the blend shapes in this case? The blend shape are when you create different meshes, and these meshes represent expressions, and we mix these meshes to create a final face. It's a principal idea about the blend shapes, okay? And again, about when we use this technology, for example, I talked about the Golem and the Lord of the Rings, and here in this slide, we can see the example about Golem. Look about the movements and the capture. It's we can see in the movement in the slides when we change the values in the red labels, and when you change the values, we can change the expression together. Okay, the idea is you create a lot of meshes, use the different values from the mesh in the mix all together. Okay. Okay, but about the blend shape, what meaning of mix the blend shapes? The idea is sum the meshes, and in the end, this sum creates a virtual face. And we can see the picture. There are some vectors to represent the meshes. The first vector is about the neutral faces. What's meaning of neutral face? Neutral faces, the face don't have expressions. Okay, and the other vector represents the meshes. And the idea is discover what these meshes look like. The capture, I mean the sum these mesh together. Okay, the the principal idea about the use blend shapes. The other reason to use a lot of blend shapes, and it's easy to find the tools to use this technology, and they use it to modeling these meshes. We can see in the slide the example about this. For example, in the softwares, there are software to use sliders, and these sliders represent the expressions, and we can change the value, and the same time we can change the face. Okay, here in this slide you can see the example about the facial animation when the actor, I don't know, maybe it's a camera capture the actor, open the mouth, close the eyes, etc., and the virtual face imitate the human face. Nice. And the other stage from the facial animation, it's a capture. In the capture, you have the two principal methods, okay? We have the optical methods and then we have the automatic methods. What's the difference? The difference is optical methods, it's a idea when we use some points in the face, but we need to draw these points in the face and use some cameras to capture these points. The problem is the manual working. Every time is necessary to create these points in the actor face. The second method is automatic. In this case, we can use some algorithms, some libraries to capture the same points, but is automatic. You cannot need to draw this point in the face, okay? And in this case, there are the two approaches. Um, in the capture stage, the we can use some special cameras, for example, RGBD. This camera can capture the deep reference in the virtual world around the camera, okay? And in recent works, uh, I can see the people use the webcams when you can capture the 2D photos, okay? It's possible too for this, for to create the facial animation, okay? And in the last stage, it's a retarget. What retarget is facial animation is the same. The idea is put all the steps together, in the end, create a realistic face. Okay, it's the last step to create the facial animation. Okay, I'm going to try to explain the traditional approach about the facial animation. The principal idea is using this technology to automatize this process because before this technology, the process is manually and it spend a lot of time because the traditional approach, we in the it's common to use professionals to create these characters using softwares, not using the automatized process, okay? And the other hand, when we start to use a blend shapes, the bring a big advance for this technology because blend shape it's easy to use and it's fast because it's only a sum of vectors. In the next slides, I'm going to try to bring more information about the traditional approach and about algorithms to compare this kind of face, okay? Nice, go ahead. Okay, uh, the algorithms are used to detect whole similarities in the expression that represents the mesh of a set with the capture face, okay? This is done through a calculation that determines the difference between the capture reference points and the reference points of the mesh being compared. The closer this distance, that is, the closer it is to the zero value, for example, more relevant it is, and the more it's weight it's giving when making the sum between the meshes. And algorithms widely used in this phase, for example, Euclidean distance. Okay. The Euclidean distance it's a, a distance Euclidean. The Euclidean distance it's measured that calculate the distance between 2 points in a 2D vector space. The smaller this value, the closer the points are. What's its meaning? For example, we have the capture. You use some marks in the capture and use the similar marks in the virtual face, and we detect the distance between these points. Okay, the smaller value represent this capture. It look like the virtual face. There are others algorithms, for example, um, interactive close points. In this case, the interactive close point was developed to join meshes that have similarities. What for this happen? It detects point in the meshes and calculates the distance between them. In this case, this algorithm is used to merge the similar meshes, but we can use these algorithms to detect the distance between the meshes or between the points. Okay. In this case, it's same about the Euclidean distance. And the other algorithm is very famous. It's Haldorf distance. The Haldorf distance, the max distance from one set to the closest to the points in another set. It's a metric using various types of computer vision applications such as image match, moving object detection, for example. Okay, and in the last algorithms, not the last in general, but the last I'm going to present, it's a PCA, Principal Component Analysis. Its algorithm, it's a statistical analysis technique. It's a statistical analysis technique used to compress, visualize, and short data, reduce the dimension of dataset with a minimal loss of information. Okay, and these algorithms can be used to compare points of capture face, its points of generate meshes. Is the same. The smaller the value, the more similarities the mesh are to the analyzed face. This algorithm, it's a huge use. It's using a lot in this technology because imagine if you have a lot of points in the face and a lot of points in the mesh, you can reduce the size and compare only some points, not all the points. In this case, this comparison it is very very fast. Okay, machine learning. The facial animation is today using a lot this technology, the machine learning, to create this virtual face. Okay, the idea is you training some algorithms to detect the face and detect the expression and move this expression for in a virtual face. Before to start speaking about the facial animation using machine learning, I'm going to bring some concepts. Okay, nice, go ahead. Okay, machine learning are techniques used to make computers make decisions about certain topics. This can be done in a supervised and unsupervised manner. In both cases, there is a prior training to generate the so-called neural networks or classifiers that you will be able to identify behaviors between some things. Okay. When we talk about the supervised training, we have a set of labeled samples. That is, sorry. Identified. For example, if you have several types of dogs and you identify which one by it's bred, we can train a classifier. It's a supervised way to automatically identify the breeds of dog. Okay, it's the principal idea about the supervised training. And the other use, now when you have several unclassified samples, for example, you have to do an unsupervised training where we will create a way to group the sample by similarities. That we must group the samples by similarity characteristics and create what you call clusters. Okay. How to use machine learning in facial animation? Now, knowing how classifiers work, the idea is to use this technology in facial animation, and that what happened with most surveys. Okay, in the end, we will have a training network that given a capture of an image, for example, can identify in a set of expressions which can be mixed to compose a virtual face, okay, similar to the capture. With this, we can make facial animation using artificial intelligence techniques. Um, for example, imagine a training network that receives a face as input, and we can see in this slide the capture, and in the middle it's a networking to detect this expression. Okay, this network is classified by expression types, where each mesh also has the same classification. And in this case, you create similarities between the samples in a neural network and the meshes. With this, the results of this network will be which expression make the most sense to generate the final virtual face. Okay, and the idea is capture, test what about the similarities in neural network, discover what mesh represents this face, and move this this face to the virtual face final. Okay, but it's an important thing to train in the network or a classifier is the definition of the features. I think the definition of the features is the most important steps to create a neural networks. Okay. There are several ways to do this. Some jobs use the facial markers, obtain the capture phase. Others use the texture of colors that are found in certain regions of the face, such as the mouth and the eyes. In these steps to create definition of features, it's very common to use it, for example, some libraries to capture these features in the face, and they use these the name is a vector of features to train the neural network. Okay. For example, in this case, in this slide, I show the name DLib. DLib is a famous library to detect the points of face and extract these points. And it represents a face in this moment, okay, in the moment of the capture. Okay, but there are other important features. In additional, for example, the classification of the samples, it's also important. Okay, for example, it's a very common for samples to be sorted by expression types. In this case, we use the ECMA classification. It's widely used. It predicts for each region of the muscle of the face the junction of these regions form the expression. Okay, it's we can see in the slide the example about this classification. depending the region of the face, this classification uses a label. And for example, we can see the eye region. We can see a label inside the photos. The label represents this region in a classification of Ekman. Okay. And another important point in this creation of it's a creation of sample database. It's necessary to choose foundations that have different types of expressions, genres, and the types of face, such as Westerns or Westerns face, for example. For research, there are a number of labels. For access, it's necessary in the most cases to fill out your forms or receive authorization for use. For academic use, the bases are free. For commercial use, some charge specific amounts for each type of the use. And there are a lot of kind of databases, user faces, and the most of database it's free, okay? And depending on the database, there are different characteristics. For example, we can find the database to have a lot of short movies, short videos, or there are a data set of photos, different expressions, and we can use this to create this data set and extract the features and the training the neural network. Okay, and the last stage when you're going to create of facial animation, uh, it's a create a pipeline to manage these steps. Okay. And the last stage of facial animation is done online. After capture the face, as analysis is made by a training classifier that generates the weights. In the end, these weights are applied to the meshes that generate the final face. But for all these steps to happen, there are online steps that takes place beforehand and prepare to the data for training. Okay, in this technology, it's very common to use two steps to create this. The name is pipeline. This process. The first step is totally offline when we train the neural networks. Okay, we uh, pick up some data sets, create the features, etc. In the steps, it's very common you identify create a base face, for example, a neutral face to use to define the base to some the other meshes when you're going to create a final face. In the online process, it's when you're going, in fact, create the virtual face. When you are capture for example, a video in real time, calculate the weights between the meshes and the capture, and the redirect make the retarget to the final phase. Nice. Okay. In this part, this presentation, I'm going to bring the different kind of features to use in facial animation. For example, the Nishimura method. This Nishimura, in additional to facial marker, he uses the sound to identify expression. Okay? The tone of voice indicates a type of situation that causes the expression to change. In this case, this feature is important because prevent the sound not prevent, for example, when you're going to capture the face, there are some problems about the block, the points, or for example, the hair inside the face block some points in part of face. In this case, voicing, no. and permit you creating using these features in facial animation because we can identify the expression using the voice. The next method, the Abdelaziz method, uses the same approach, use the sound as feature to create a neural network to identify the expression and create the virtual face in the end. Okay. In the last part of the presentation, I'm going to bring some examples about the facial animation. The first example is about the Zoe. Zoe, it's a virtual animation. It's a woman, and they use the facial animation techniques. Okay, go ahead. Yes, amazing. We can see in this animation the actor has a helmet in your head, and this helmet fix the image from capture, and in this when this helmet capture the face, the helmet this detect the points in the face in the other reference to create this realistic animation. Okay. The next example it's about the facial animation, but we create this animation to test a classifier, the name OPF. The OPF uses algorithms to detect the distance between the points and use graphs. Okay, it's a very fast algorithm. In this case, this animation is very, very simple. Yes, it's very simple, it's very fast. In this case, for this animation, we use only 2D images and the facial points, okay? And in the last, oops, in the last example, we use the Unity. Unity is a software create a games, very famous. And the idea is test if Unity can use the blend shapes and create the virtual face using this technology. Yes, it's possible. We create a plugin in the Unity and create a client to connect in this plugin inside the Unity and send informations during the capture. This example, it's a bit slow, but we're creating a real time. Okay, nice. Go ahead. Yes, there are some delay about the capture in the facial animation, in fact, but it's because we use a small quantity of frames to create this animation. Okay. 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 Thank you very much for the opportunity to bring this technology, to show this technology. But before the end, I'm going to show a small video. In this video, we bring the history about the facial animation in video game. Okay, enjoy and thank you very much.
Pixels to polygons, simple to systematic, indefinite to detailed. The faces we see on video game characters have gone from basically up to your imagination to accurate material, skin, and hair simulations. And today GameRanks wants to take you on a little trip through the evolution of facial animation in video games. So way back in 1980, before even I was born, that's right, old Falcon's a millennial. You did know that's the cutoff point, right? 1980? And if you include the year 1980, you might be surprised to find out that Pac-Man is actually a millennial as well. That little yellow pizza with a missing slice is also pretty much the first example of, dare I say it, detailed facial animation in a video game. Now, obviously, to call Pac-Man's facial animation detailed, you have to broaden your idea of what detailed is for a moment. But you also have to remember, we're trying to go back as far as we can. Before Pac-Man, there really wasn't anything that you could even call facial animation. It's not as though he had an incredibly detailed set of expressions that he gracefully transitioned between, or anything like that. He just used more than one frame to change expressions. His range of expressions was pretty limited and included open mouth and shut mouth, but for the time it actually was very smooth animation, at least for a video game. Slightly more detailed but less smooth a year later was Donkey Kong. Now, Donkey Kong didn't really have any transitional frames in his face, but depending on what actions he would take, he had very different facial expression, pretty detailed ones considering the low resolution. You knew what Donkey Kong was thinking as he lobbed those barrels. You knew the frustration that he felt. He was obviously a gorilla, but he was also just a squirrel trying to get a nut. I'm going to allow you to contemplate that for a moment, and then think about what Donkey Kong actually is. Oh yeah, you figured it out, didn't you? It's a horny gorilla. I guess it's probably better that frustration's really kind of the only thing we saw of Donkey Kong, right? It's a good thing we aren't seriously entertaining the idea of an animated O-face on a monkey in 1981. But for the rest of the 1980s, the believability of a character's face was generally kind of left up to the player. Essentially, games like Legend of Zelda and Super Mario Bros. Didn't really give you facial animation per se. They kind of gave you a pretty blank-looking face and kind of left the human subconscious to fill in the blanks. In a way, video game characters' faces were slightly abstract art. On account, abstract art depends upon the outlook of those viewing the art to give the art meaning. In the era of very low detailed games, this was generally the right thing to do. In a game like Legend of Zelda, your character is very small, one tile of the game in size. You don't really want to occupy the screen with a large amount of face. It would probably look pretty weird. But every once in a while you would have a game like 1987's Mike Tyson's Punch-Out!, where the developers were provided an opportunity to have a larger character on the screen and give different facial expressions. All things considered, Mike Tyson's Punch-Out! Probably has the most detailed facial animation of any video game in the 1980s. Considering that's an entire decade of gaming, that's actually pretty impressive. And if you look back, obviously now the games of the 1980s, especially the 8-bit games of the 1980s, are looked back as retro now, or even quaint or kitschy, depending on what region of the world you're from. You have to consider that nothing like that had ever existed. The Earth has been around for 4.5 billion years. The concept of a face is relatively new, let alone the concept of facial animation in video games. So let's take a moment and recognize the important steps that were taken in the 1980s to define exactly what a video game could even be. We wouldn't be talking about things like the uncanny valley today, which represents the difference between our incredibly detailed simulations of the world and the actual world. If technology hadn't existed, that frankly looks like crap compared to what we see now. Obviously, we aren't talking about massive advances at this point because we're really looking at tiny sprites still. But a notable advance, I would say, came in the form of Sonic the Hedgehog in 1991. If you left Sonic alone for a while, he'd get impatient. He'd stand there and he'd tap his foot and he'd look at the player like, you gonna do anything? You gonna go on? You're playing this game for real, right? You didn't just turn it on and walk away, did you? Visibly irritated by the fact that he had to wait for the player. The following year in 1992, a game called Wolfenstein 3D came out. Now, there is a massive amount of technological advances as well as advances in the paradigm itself, but focusing just on faces in the game, they featured a face showing what your face was doing, supposedly, in-game at all time. The Wolfenstein guy's face reflected how much damage you had. He sort of peered around and appeared to be animated and full of life in a way that maybe you wouldn't expect. In 1993, Doom, basically the successor to Wolfenstein 3D, expanded on a lot of engine ideas, from texture mapping to surfaces being different heights, etc. But they also went in and made the Doom Marine's facial expressions even more expressive. He reflected damage still, but he also got pretty aggressive sometimes, which was neat. It was cool to have your in-game avatar sort of representing what you might feel at the time, at least what you would feel in sync to what's going on in the game. Given the relatively small capabilities of machines at the time, both console and PC, that's kind of about as far as it got. That all changed, however, with the PlayStation and the Nintendo 64. It's actually their mascots, their flagship characters, that kind of did it too. When you first pop in the Super Mario 64 cartridge, you're greeted with Mario, and he's like, yeah, I'm Mario. Check it out. I'm a fully animated polygon face. My eyes are fully functional. My ears move. I can smile. I can talk a little. Oh, and you can manipulate my face with a cursor if you are so inclined. The jump in technology that was made for facial animation in video games that happened between 2D games and Super Mario 64 is astounding. Now, Mario had a few in-game facial expressions, but generally stayed pretty static. A game that came out just a few months after Mario 64, Crash Bandicoot, was not that way. Crash actually would constantly change facial expression, to the point where it was actually amusing. I was amused by Crash Bandicoot in the way that I was often amused by cartoons at the time, and that very much turned me on to PlayStation, because technically it was a less powerful machine. Why would you want the less powerful machine? Well, obviously, just because the graphics aren't quite as good doesn't mean the games aren't. And believe it or not, that little thing was actually what told my kid brain, hey, it's okay to like the less powerful machine. It's about having fun, right? And believe it or not, things like Crash Bandicoot's facial animation actually made me consider that idea. In 1998, Half-Life came out, and Half-Life did a lot of very different things, especially in the first-person shooting genre, where when you went back a few years, the only facial animation was that of a sprite depicting what was going on the face of the player character. Pretty much everybody had various expressions, not anything too astounding, but everybody talked in a manner that actually changed the polygons on people's faces. Mouths were actual holes. That same year, Metal Gear Solid came out, and it contained sprite animation that happened in dialogue moments where you went into the codec and spoke to other characters. This is probably one of the last mainstream uses of 2D graphics to depict what was going on people's faces, on account technology was about to rapidly progress. Over the next few years, we'd see evolution from titles like Conker's Bad Fur Day, Max Payne, Final Fantasy X, and probably one of my favorite titles of the time, Metal Gear Solid 2: Sons of Liberty, and games that would just employ various techniques to show us exactly what was going on inside a person by showing us subtle changes in their facial expressions. In a way, the title screen to Mario 64 in 1996 kind of served as a tech demo for the next 8 or 9 years worth of facial animation in video games. Obviously, in actual gameplay, generally nothing looked as detailed or interesting or animated as that title screen, but everything was sort of working its way to that point. And by 2004, nearly a decade later, Valve, the creators of Half-Life, had come up with something that was the next huge step in facial animation in video games. Where Half-Life 1, which by all accounts, like I said, a landmark title in video games, ran on a highly modified version of the Quake engine, Half-Life 2 was being developed on entirely proprietary technology that Valve had been working on for quite a long time. In 2004, when Half-Life 2 came out, it was our first official interaction with the Source engine. Now, why this is so important is the Source engine has a very specific facial animation system inside it. You could easily rig a character model that you had created with a movable face in a way that allowed you to manipulate the face in an incredibly easy way and standardize the facial animation for all the characters. No longer did it have to be, okay, you make the smile for this character, now make the smile for this character and this character. You could apply the same action to an internal structure that simply manipulated every single one of these models in the same way. And what this did was change the amount of work that had to be done in order to make all the characters animated, specifically in the face. These types of techniques were adopted by almost everybody almost immediately, and many games from that point forward used this kind of rigged animation system for faces as well as basically the entire body. And I know that Half-Life and the Source engine aren't the absolute first instance of using a rig in order to create animation, but in video games it is most certainly the most noticeable, the most notable, and the title that did the most to popularize the technique. A lot of different games used a lot of different experiments on other ways to do it as well over the next few years, but generally it sort of stuck to that, or at least variations on that. However, a game came out in 2011 that pushed the boundaries so much further than anybody had on what could be done on a face, and did it in a way that nobody really has attempted to do again since, and that's LA Noire. Now, the way the facial animation was accomplished in LA Noire was actors sat down with a bunch of high-definition cameras strapped to their face and acted out all these scenes. Animated maps were created from these cameras and mapped onto polygons in-game that replicated the performances. The result is an incredibly detailed style of animation that, in all honesty, was rather astounding. But at the same time, it was also a little strange looking, being that everyone's face was kind of constructed in a manner that was based on capturing an image of an actual face doing all of the things and mapping it onto something that didn't look entirely real. The game looked a little strange too. That's not to detract from it. At the time, this is the absolute pinnacle of facial animation, and there's nothing you can say to contradict that I think would be valid. That being said, the fact that the game was a stylized, polygonal, almost cartoon with these hyper-realistic face textures, and also combining the fact that the hardware of the time wasn't necessarily creating realistic lighting, at least in the way it's done now, it could produce some rather strange results. It was impressive and it was cool, but it also kind of taught a little bit of a lesson, and that is that until we actually can synthesize reality, it doesn't really make sense to try and place real things into an unreal world. To bring up the uncanny valley again, LA Noire was not just the pinnacle of facial animation for the time, it was also peak uncanny valley. All of the times that motion capture had been applied to a face culminated in and created kind of maybe a little bit of an awkward, not quite one-to-one representation, culminated in LA Noire. And the lesson learned is maybe that it doesn't hurt to not attempt photorealism in the face. Some element of stylization really should be present in art. You know, style. And that was only 5 years ago. Isn't that weird to think about? Games look infinitely better now. And I think LA Noire actually directed a lot of that, in that people understood the necessity for very realistic animation, but when you try too hard to look real, it ends up not looking real. And to that effect, you saw more games like The Last of Us, Tomb Raider, and BioShock Infinite, where the real effort was put into how people moved rather than how realistic they looked. The techniques that are in place are actually not that different than they were or in 2004 with the Source engine. They create people and then rig them in various ways, bone systems and muscle systems, to implement a way to animate them, and in some cases they're motion captured. Facial capture is now done in a way that can be tracked much more accurately, and that animation can be put onto a character without it looking super weird, but really that kind of entirely hinges on hardware evolving and making it possible to show more polygons and light them more realistically. A lot of what we attribute to people getting better at animating faces is actually just technological advances that may not even have anything to do with facial animation. Just the game itself looking better can make the facial animation look better in context. Uncharted 4 just came out, and believe it or not, they actually use the facial capture as a basis, doing a great deal of the animation by hand. And in my opinion, this is the best case you could possibly make for doing all of these types of things by hand. Not worrying about them being realistic, but rather worrying about them being stylistic. Yes, rigging systems are used in order to do the facial animation. In fact, Naughty Dog is saying that over 300 to 400 bones are implemented in each one of the characters' faces. But when you're not worrying about being entirely true to the performance, when your goal is really just to start there and from there move into a much more context-sensitive style of animation that suits the world it's in, I think it just looks much better. And again, until we can synthesize reality itself, I don't think there's a good reason not to be treating facial animation as art. Going forward, I'm sure that there's going to be a lot of times when people use facial capture in a way that looks great, but I'll be honest with you, I think an artist's eye for what looks right in an in-game world is going to produce the best facial animation going forward, at least for quite a while.